Problem number 22. A block of mass 2m is placed symmetrically on two identical wedges of mass m as shown. All surfaces are frictionless, and the wedges have angle theta to the vertical. If the system is released from rest, what is the downward acceleration of the block? Solution for problem number 22. In this problem, it's not easy to make forces approach to solve this problem, because point of contact is infinitesimal, and it's not easy to find what is the direction of forces between these masses. But here is better to use energy approach. Suppose that block 2m move to height h downward. So in that case we can find that the change of potential energy equal to 2mgh, and this potential energy converting to kinetic energy of all three blocks. Suppose that after that speed of block 2m is v. Using trigonometry we can find that horizontal speed of blocks m and m are v1 equal v multiplied by tangent theta. So from energy conservation we can write that 2mgh equal mv square plus mv1 square. And using this relation, that will be this expression or this expression. So it means that v square equal 2gh cosine square theta. But from other hand, we know that during motion with the constant acceleration, we have relation between speed, acceleration, and distance like this. V square equal 2ah. It means that acceleration a equal g cosine square theta. This is answer E, and that was solution for problem number 22. Problem number 23. For objects moving through air, the force of air resistance can be modeled as proportional to the speed, linear drag, or proportional to the square of the speed, quadratic drag, depending on the circumstances. Two identical objects A and B are dropped from the same height h simultaneously, but object A is given an initial horizontal velocity v. The objects hit the ground at time ta and tb. Accounting for air resistance, which of the following is true? Solution for problem number 23. For linear drag, the horizontal and vertical components of the motion are completely independent. So we have ax equal negative bvx and ay equal negative g minus bvy. So it means that for both cases we have same vertical equation, and it means that ta equal tb. For quadratic drag we have acceleration ay equal negative g minus b vy multiplied by absolute value of v. It means that in case A we have a greater air resistance, and it means that Ta greater than Tb. That's answer C, and that was solution for problem number 23. Problem number 24. A satellite is in orbit around a planet of mass big M. Its maximum distance from the center of the planet is d, and at this point it is traveling at the speed of v equal 1/2 multiplied by square root from gm over d. What is the area of the satellite's orbit? Solution for problem number 24. This problem could be solved using two main properties for orbital motion. First, it's about connection between total energy and the semi-major axis. And second is third Kepler law, connecting period of motion with semi-major axis. So first let's count what is total energy. In furthest point, it's equal to kinetic energy 1/2 mv square, the potential energy gmm over d, which is equal to negative gmm over 2a, where a is a semi-major axis. So here we can use expression for velocity for speed v, this one, put it in this equation and find that semi-major axis could be counted using d. That will be 4/7d. Now let's use third Kepler law. From this law we can write that period equal 2 pi multiplied by square root from a cube over gm, and here we can put expression through d. It will be this one, and finally we can count what is the area of this ellipsis. According to the second Kepler law, satellite sweeps the area with a constant speed. It means that this speed equal 1/2 distance multiplied by speed in the furthest point, which is 1/4 multiplied by square root from gmd. And now we can count what is total area. That will be this constant rate, delta A over delta T multiplied by period. And after calculations we will get this expression, which is answer B. That was solution for problem number 24. Problem number 25. A cylinder is placed with its axis vertical, and the rubber band of mass m and tension T is wrapped horizontally around it. What is the minimum coefficient of static friction μ between the rubber band and the cylinder such that the band will not slide down the cylinder? Solution for problem number 25. Let's consider a small piece of rubber band on this picture. Suppose it takes a small angle theta, and we can write equation for horizontal equilibrium of this piece. So it means that projection of this two tensions T on vertical must be equal to normal force, which is normal force equal 2T multiplied by sine theta over 2, which is for small angles approximately T multiplied by theta. From other hand, we can find what is force of friction. That will be μ multiplied by this normal force. For equilibrium, we have mass of this piece, which is m multiplied by small angle theta over 2 pi multiplied by g. That must be less than μn, which is μ t theta. And from here we can count that μ must be greater or equal to mg over 2 pi t. It means that this is the minimum for coefficient of static friction. That's answer A, and that was solution for problem number 25.